Good evening to all. Welcome to the 17th lecture of the course Experimental Methods in Thermal Engineering. In the last lecture, we did discuss on the measurement of the pressure, and in today's lecture, we'll continue our discussion. So, in the previous lecture, particularly, I have mentioned that while we are having a transducer, in a transducer, first we are having some sensing element which actually senses the pressure of the fluid, and depending upon that, we are having some elastic deformation of the mechanical material. Okay, then we use certain devices in order to convert that mechanical deformation into the electrical signal, and in particular, I have specified you about the principle of the strain gauge, and there also mainly we have discussed about the resistance type strain gauge, where the local strain produced in a mechanical component is actually converted into the electrical signal in terms of its resistance value. Okay, so then we have started discussion on the measurement of that resistance, and particularly for the measurement of that resistance we have actually employed our fundamental concept from the basics of Wheatstone bridge for measurement of the unknown resistance. Okay, and particularly in balanced conditions, I have considered as the resistance of the strain gauge, and particularly this R1 is actually nothing but the variable resistance which can be tuned in order to balance the overall circuit, and from the balanced condition we will be getting nothing but R1 divided by Rx equal to R2 divided by R3. Okay, and using this relation, because other resistances R2 and R3 are known, and R1 by varying, though it's nothing but variable type resistance, but we know its value also. So I can determine the value of unknown resistance Rx as nothing but equal to uh, R1 into R3 divided by R2. Okay, so this particular condition will be only applicable when the bridge is completely balanced. Okay, so this type of manual balancing of the bridge can be employed when we are having the measurement of static type. Okay, if we are going for the dynamic measurements, then obviously we will not be having the sufficient time in order to balance our Wheatstone bridge. Uh, and before that, our physical value of the pressure will be changing, which will be actually changing the resistance of the strain gauge. Okay, so ultimately what we require certain system which can determine the value of unknown resistance at the time scale, which is actually smaller in comparison to that of the time scale of actual pressure change of the phenomenon. Okay, so under such circumstances, what we do, we don't go for the balanced circuit, rather we go for the unbalanced circuit. So it means in case of unbalanced bridges, what we will be doing, we will try to determine the value of this voltage or current unbalanced, whatever we are getting across our galvanometer. Okay. So particularly if you see what we are having over here, EB is the supplied voltage from the battery and RB is the resistance of the battery. Okay, and then obviously what will be happening, because of this RB resistance we will be getting certain E amount of only E amount of effective voltage across the bridge. So this E is nothing but we are calling as effective voltage, which is actually acting over our Wheatstone bridge circuit. Okay, and in this particular circuit what we are having, we will be having one of the resistance as unknown. So for example, I can consider, say, R1 is my unknown resistance, which is nothing but coming from the strain gauge. Okay, and other all three resistances we can take as known resistances. Okay, so what will be happening, while we will be having certain mechanical deformation of the diaphragm, in that case the value of R1 will be actually changing depending upon the amount of the deformation, or I should say depending upon the local strain which will be produced in the location where our strain gauge is actually attached. Okay, so in this particular type of circuit, if I consider that the resistance of the battery is not influencing our remaining circuit, that particularly happens when we are having the slightly small unbalance. So in that case, what will be happening? whatever the current which is actually passing through this galvanometer. If I call this current as Ig, that Ig will be nothing but equal to Eg, where Eg refers to the galvanometer voltage. Okay, so whatever the voltage will be, the difference between point A and point C, divided by R. If I call R as nothing but equivalent resistance of these four, R1, R2, R3 and R4, plus Rg, which is the galvanometer resistance. So that will be the amount of current which will be passing through the galvanometer. Now if we have to determine, so what is this R? This R is nothing but I am considering as the equivalent overall resistance of this circuit. Okay, and particularly this overall in unbalanced situation. But the only condition we consider that circuit is slightly unbalanced. Because of that, we are considering that the resistance of the battery is actually not influencing our circuit. Okay, so that is the assumption over here. So this R, I can call it as nothing but equivalent resistance. So this is my equivalent resistance, and particularly this equivalent resistance will be acting when our circuit is actually unbalanced. Okay, so we are not considering that our circuit is fully balanced, because if our circuit is balanced, in that case there will there will not be any current flow through this galvanometer, and the galvanometric current will be equal to 0. Okay, then what we want to do over here now, if I find that what is the value of Eg, so obviously the value of Eg will be nothing but equal to, so here Eg refers to the galvanometric voltage. So galvanometer is connected across the terminal points A and terminal point C. So that will be nothing but equal to potential at point A minus potential at point C. Okay. And over here you can see that this entire circuit is actually subjected to total effective potential E. So what will be happening? Some fraction of the E will be actually contributing the voltage across R1, and some will be contributing to voltage across R4, and some will be actually contributing over here also, because in unbalanced situation we will be having the flow of current over here also. Okay. So now using the voltage division rule, what we can do, we can determine the value of potential across point A. So as per the voltage division rule, potential across A will be nothing but E times R1 divided by R1 plus R4, because over here if you can see, this E is actually contributing particularly for R1 R4 in one parallel connection, and in another parallel connection it is contributing for R2 and R3. Okay, so this will be E times R1 by R4 minus of E times R2 divided by R2 plus R3. Okay, so this term is nothing but, this entire term is our equivalent to voltage at point C, and this first term entire, it is actually equal to voltage at point A. Okay, so using this particular formulation, I can determine the value of Eg. Okay, so this is the value of Eg, and this is the value of Ig, and in this Ig, so obviously whatever we are using over here, galvanometer resistance will be known, and this R refers to the equivalent unbalanced resistance whatever we are having out of all these four resistances. Okay, now one important thing we have to determine, so I have already told you that if Eb is the battery voltage, out of that only E fraction of effective voltage we will be getting over the circuit. Okay, so if we consider that for small unbalanced situation, so now what we are considering that we are having very small unbalanced situation. So it means in case of very small unbalanced situation, I can consider that my galvanometric current is nothing but tending to 0. So if my galvanometric current is tending to 0, in that case what will be happening, whatever the current I will be having over here, same current will be actually passing through this resistance number 4. So I4 will be equal to nothing but I1, and similarly whatever the current will be passing through I2, same current will be coming to R3. Okay, so it means I can simply consider that my galvanometer now is actually not connected to my circuit. Okay, so this condition will be applicable when we are having very small unbalanced situation, and Ig is actually tending to 0. Okay, so under such conditions, what will be happening, if I try to see the equivalent circuit of the resistance, these two resistances R1 and R4, because now I am considering that this galvanometer is not connected. So this R1 and R4 will be considered as nothing but series resistances. So I'll be getting one equivalent resistance as R1 plus R4 and another equivalent resistance of R2 and R3 as series. So that will be coming as R2 plus R3. Okay. And now overall, if you see, this overall resistance of R1 and R4 is in parallel with overall resistance of R2 and R3, and that entire is actually subjected to voltage E. So it means overall resistance of the balanced circuit. So now particularly this overall resistance, when I am writing this, I am writing for a balanced circuit. Okay. So nothing but now my R1 plus R4 and R2 plus R3 are in parallel. So my overall resistance of the balanced circuit will be equal to R1 plus R4 times R2 plus R3, and divided by, we will be having R1 plus R4 plus R2 plus R3. So that is my overall resistance. So this is the overall resistance, and then we are having some resistance because of the battery RB, and then that is actually subjected to some connected to a total supply voltage of EB. Okay, so it means finally, if I try to see, a balanced circuit will be something like this, where we are having a battery, then we have the resistance RB, and then we have one overall resistance of balanced circuit as RO. Okay, and what we are considering, that across this overall resistance, the voltage we are getting, that voltage is nothing but equal to E. Okay, so from this particular circuit, I can write that my voltage E will be nothing but equal to EB times RO divided by RO plus RB. Okay, so this point is clear. So by considering a completely balanced situation, we can determine that what fraction of the battery voltage is actually effectively acting over the circuit. And once we are knowing this effective voltage, then using this effective voltage, we can actually determine the value of our galvanometric voltage, which is acting across the ends where galvanometer is connected, and then using the overall equivalent resistance of the unbalanced circuit along with the galvanometer resistance, we can determine the value of galvanometric current. Okay, so ultimately what we are doing over here, in case of unbalanced circuit, we are basically not controlling the value of R1, rather because of the R1, whatever the change is happening in the value of output voltage or current which is acting across the galvanometer, that we are actually measuring. Okay, so it means what we have to do now, we have to somehow relate the change in resistance with the change in voltage or change in current of the galvanometer. Okay, so that let us try to see in the subsequent slide. So now we are having this unbalanced circuit. Okay, now in this particular unbalanced circuit, I have considered that R1 is my the resistance because of the strain gauge. So obviously, if I consider the voltage across the galvanometer, I have already specified you EZ, or I can call it as ED also, where this subscript D is nothing but it is referring to the detector. So you have to be very careful. This D is not referring to our terminal point D over here. This actually refers to the detector over here. So we are calling the detector voltage is nothing but E times, where E is the effective voltage which is acting on the circuit, divided by E multiplied by R1 by R1 plus R4 minus R2 by R2 plus R3. So this I have told you in the previous slide. Now what will be happening? So this is corresponding to some given value of R1. Okay. So now when we will be having certain localized strain in our strain gauge, because of that what will be happening? There will be change in value of this resistance. Now let us consider that we are getting the new value of resistance as R1 plus delta R1. Okay, so there is a change of delta R1 in the value of the resistance of the strain gauge. Okay, so because of that, what will be happening? If say initially I was getting some ED1 as the voltage across the galvanometer, so now I will be getting certain change in that voltage. So say now let us consider that delta ED is the change of resistance across the change of voltage across the galvanometer. So delta ED divided by original, so this is nothing but this E I am taking to the left hand side, so I can write delta ED by E will be equal to nothing but R1 plus delta R, because this R1 resistance is only changing and all other resistances are known. Okay. So from here, our aim is basically, while we are actually determining the value of the pressure or value of the strain is having direct relationship with the change of resistance. So ultimately, what we have to do, but over here, what we are doing from the circuit, we are getting nothing but our output voltage. Okay. So what we have to do now, we have got some relationship in between the change of voltage and the change of resistance. Now what we have to do, this change of voltage actually we have to write in terms of the change of resistance, which is already written, but ultimately our aim is to determine the change of resistance corresponding to the change which we are getting in our voltage. Okay, so nothing but what is done over here, this entire equation is rearranged in order to find the value of delta R1. Okay, so if we just rearrange this equation, upon rearranging we will be getting the value of change of resistance delta R1 divided by R1 equal to nothing but we will be getting by using this equation. So now in this particular equation, if you see, the value of R4 is known, R1 is also known, because R1 is nothing but it represents the resistance of the strain gauge corresponding to the no strain condition, and that is something which is actually provided by the manufacturer of the strain gauge. Okay, and E is the effective voltage which is applied across the circuit, and this delta ED is the amount or change of voltage which will be happening while we will be having actually uh, the change in the strain of our system, and that change in strain will be actually changing the resistance of the circuit. Okay, so what we will be doing normally while we design the circuit, so it is designed in such a fashion so that during the neutral situation we are getting nothing but zero voltage out of the galvanometer, so it means it is set to the neutral position. So with reference to zero, when we will be having any deflection, that deflection will be nothing but identical to that of delta ED. Okay. So in this particular case, what we are doing basically, we are having an unbalanced circuit, and in the unbalanced circuit, we are measuring the value of delta ED, and that value of delta ED, means change of voltage across the detector, is actually related using the known values of the resistance and the supplied voltage to find out the change in resistance. And we know this change in resistance with the help of a known value of the resistance of the strain gauge, and the gauge factor can be related to the corresponding value of the strain. Okay, and that particular value of the strain is having linear dependence on the pressure, so obviously we can relate directly over here the pressure and particularly the voltage signal whatever we are getting. Okay, so this is one of the way where we are actually dynamically measuring the voltage across the galvanometer, and using the galvanometer, and this voltage is actually related to the value of the pressure. Okay, now another way could be, instead of measuring the voltage, we can measure the value of the current also. Okay, so I have already given you the formulation of galvanometric current in previous slide, where I have told you that Ig is nothing but equal to Eg divided by R plus Rg, where this R refers to the equivalent resistance when we are considering unbalanced circuit. Okay, so if we, and Eg also, I have given you the formulation of Eg where it is actually related in terms of E. Okay, so now if we use this particular formulation which I have discussed in the previous slide, and if we find out the overall equivalent resistance, finally we will be getting the value of current Ig as nothing but E times R1 R3 minus R2 R4 divided by this entire big term in the denominator. Okay, so in this entire term you can see this value of Rg is known, R2 and all the four resistances R1 R2 R3 R4 are known. Okay, so now what will be happening when we will be having certain amount of strain, because of that strain there will be change in value of the current signal. So we will be finding delta Ig, and that delta Ig will be mainly caused because of the change in resistance of strain gauge, so which is nothing but our R1. Okay, so we will be having some change in resistance delta R1, so our final resistance will be becoming nothing but R1 plus delta R1. Okay, so now you can see that if our delta R1 means change in the resistance, that is a small value, So ultimately what will be happening in the denominator, you can see over here we are having three terms in multiplication everywhere where we are getting R1. So obviously because of the change in resistance, we will be everywhere finding R1 plus delta R1. So in all the terms, particularly in denominator, where R1 plus delta R is involved, we are having the multiplication of three different resistances. Okay. So because of three times multiplication, what will be happening? This value, because of the change of resistance also, there will not be significant change in value of the entire denominator. Okay. So because of that, what I can do, this entire portion of the denominator, I can consider as some constant equal to C. Okay. So that is what is done over here. While we are considering that the change of the current has happened, and that change of the current has happened because of the change in resistance of the strain gauge. So we have considered this entire denominator as some constant parameter C. Okay. So now I can write it as E by C times R1 plus delta R1, because in the denominator, in the numerator, R1 is actually changing to some by amount delta R1. So R1 plus delta R1 into R3 minus R2 R4. Okay. So over here you can see nothing but we are actually relating the change in resistance directly to the change of current. Okay. So what I can do, I can use over here some emitter, and that emitter will be actually giving me the value of current, and depending upon the change in value of the current, I can directly relate it to the change in resistance. Okay. So upon further simplification over here, you can see that particularly for the balanced circuit, we will be having nothing but R1 divided by R4 equal to R2 by R3. So if we apply that balanced approximation over here, considering that balanced circuit, if we substitute the values over here, finally we will be getting that delta Ig is nothing but equal to E by C into R3 times delta R1. Okay. And this particular value of delta R1, I can simply write as nothing but equal to R1 times F into epsilon. That is coming from the knowledge of the or definition of the gauge factor, which I have told you in the previous lecture. Okay. So this delta R1 I can replace with R1 F into epsilon. Now in this particular equation, if you see, E is the supplied voltage which is constant, this C is constant, R3 is constant, and R1 refers to the initial resistance corresponding to the zero strain of the strain gauge, that is also a constant parameter, and strain gauge is also a constant parameter. So all these terms are nothing but constant. So I can simply relate the change in current across the detector is nothing but equal to constant times epsilon. So we will be getting some constant over here. So that is nothing but directly related to the strain, and strain is having direct relation with the pressure. So over here, using this particular type of formulation, we can directly relate the pressure with the change in current of the detector. Okay. So these are the two different strategies which are used by using the unbalanced Wheatstone bridges for finding out the value of pressure particularly, and that value of pressure is actually related with the current and voltage. Means either we can use the current or we can use the voltage for measurement of the pressure. Okay. So that is something which you can relate also to the practical transducer. So if you go or if you have done any measurement of the pressure using any of the commercially available pressure transducers, you might have seen that while we fix the transducer, we require some data acquisition system for recording the output of the transducer, and majority of the time you will be finding that from the transducer we get either voltage signal or we get current signal. Okay. So majority of the time current signal is generally from the commercially available transducer we get in the range 4 to 20 milliampere, and similarly there are certain transducers which are actually designed for voltage measurement, voltage as the output signal, so that voltage is also in the order of millivolts. Okay. And there are certain transducers are also available which can be employed both in voltage as well as in current measurement mode. Okay. And particularly when we purchase a transducer, commercially available transducer, so the manufacturer of the transducer also supplies a calibration curve in between the pressure value of pressure and the output value. So output may be in the form of current or it may be in the form of voltage. Okay. So many of the times you will be finding that if we plot the value of pressure in our desired range of measurement, whatever we are having, say if some transducer is measuring the pressure from 0 to 5 bar gauge, okay. So and on the abscissa we are having our current value. So you will be finding that when the current is changing from, if this current is in milliamperes, so if when the current is changing from 4 to 10, 4 to 20 milliamps, then we will be having a linear fit in between the value of the current and pressure in between this particular range of measurement. Okay, so this type of curves are already provided by the manufacturers while they actually supply this type of transducers, because what happens, we get output as current or voltage, and that output is actually then further post processed, particularly using this relation in between the pressure and current for obtaining the value of pressure. Okay, so some of the transducers give output as current and some gives output as voltage. So in terms of voltage based transducers, we will be having the value of voltage in millivolts, and over here we will be having the value of pressure. Okay, and here also we will be having linear relationship in between the pressure and the voltage. So this is also one important point. While we design any type of transducer, we actually always restrict ourselves within the linear relationship in between our output signal and the corresponding physical parameter which we want to measure. Okay, so particularly whatever the circuit I have described in the previous slide, that actually gives us some value of current and some value of voltage. Now that value of current or voltage may be very small, so because of that many of the time we require bridge amplifier circuits for amplifying the value of voltage and current so that it can be measured accurately. Okay, so for amplification we use some amplifier circuits. So here I have only shown one of the circuit just for your knowledge, but what I will be doing while we will discuss about the measurement of the temperature, at that time I will give you the detailed analysis of this amplifier circuit. Okay, so at present you can just note it down that we require certain amplifier circuit also for amplifying our output signals in order to make it accurately measurable. Okay, but at this particular instant I will not describe the entire circuit. That we will study when we will discuss about our temperature measurement. Okay, now one more criteria comes over here. So what basically happens, as I have told you in the previous lecture also, that when we measure the value of the strain, so we may have certain conditions that temperature is actually changing. Okay, so because of the temperature, what will be happening? Because of the temperature change also, there will be certain expansion and contraction of the strain gauge wire, or there may be some material of the strain gauge wire which is having dependence of temperature on the resistance change. Okay, so under such circumstances, what will be happening? The temperature will be actually leading to the errors in our measurements. Okay, so in order to avoid this thing, what is basically done, we don't go for any mathematical analysis in order to include the effect of the temperature. Rather, one more practical strategy is employed. So what is basically done, the specimen where we want to measure the strain, a replica of that specimen is actually taken. Okay, so for example, this is our specimen. So we take a replica of that specimen. So that should not be of the same dimension. So it may be of a smaller dimension. Okay, and in this particular replica, what we will be doing? So this is nothing but, I can say, a replica of the specimen. Okay, so dimension may be different, but we will be having the material as exactly same. Okay, and instead of fitting a single strain gauge, what we will be doing, one strain gauge we will be fitting over our actual specimen, and another strain gauge we will be fitting over that replica of the specimen. Okay, and so these now what will be happening, obviously this type of specimen will be actually subjected to our actual loading condition. So this will be subjected to actual loading condition because of the pressure, whereas this will be simply kept close to this specimen so that these both are in the common surroundings. Okay, so what will be happening if at any point some resistance of this particular strain gauge is changing, because it is not subjected to any mechanical loading. So this is not subjected to mechanical loading. Okay, so this particular second strain gauge is not subjected to any mechanical loading. So if the resistance of this particular strain gauge is changing, say it is changing by amount delta R2, so that change will be only because of the change of surrounding temperature, okay, or because of the temperature in which this system is actually employed. Okay, so if this change is happening, that change will be because of the temperature only. And over here in first strain gauge, which is actually employed for our actual measurement, where we are having the loading also. So here, if resistance is changing by delta R1 amount, obviously that change of delta R1 will be greater in comparison to delta R2. Why? Because here the change of resistance is actually accounting for both the effects. One is effect of temperature, okay, which will be inherent, plus effect because of the loading. Okay, so now what we can do in order to compensate for the effect of the temperature, because we want only the change of resistance because of the uh, loading only, okay, in order to make accurate measurement. So what we will be doing finally, while we will be considering the actual change of the resistance, that we will be taking as nothing but equal to delta R1 minus delta R2. Okay, so this delta R2, whatever we are getting the value of resistance, this is nothing but this will be helping us to actually correct our change in resistance of the actual strain gauge which is employed over the specimen. So if because of the temperature there is any change in resistance of the strain gauge, that we will be getting from our strain gauge 2, and that can be subtracted from the total change in resistance of the 1 in order to correct and include the effect of temperature compensation. Okay, so this is how the temperature compensation is actually taken care of in the measurement of the pressure, or I should to the pressure. Okay, so this is like all about the moderate and high pressure measurements. Okay, but apart from that, we also need to measure the pressure corresponding to the low pressure situations. Okay, so particularly what happens when we want to measure the pressure corresponding to very low pressure conditions, corresponding to that our system characteristics changes significantly. Okay, so whatever the devices we are using for measurement of moderate and high pressures, these exact principles may not be applicable for the very low pressure application. So particularly the low pressure measurement applications requires a different type of arrangement for the accurate measurement of the pressure. So that we will try to see over here. Okay, but before that, one important type of gauge is left actually for a measurement of the high pressure. So that particular type of gauge is known as Bridgman gauge. Okay, so in this Bridgman gauge, this is basically based on the principle of change in resistance of the wire depending upon the change in pressure. So what we do in this particular type of gauge, we take a container, and inside this container we will be having certain wire. Okay, and this wire will be having some resistance, say condition. Now if we pressurize this one to any other pressure more than the atmospheric pressure, so what will be happening because of the change of the pressure, there will be change in resistance of this wire. Okay, and that change in resistance of the wire can be directly related to the amount with which actually we have increased the pressure. So you can see over here one relationship is given. This R is nothing but equal to R1 times 1 plus V times delta P, where R1 refers to the resistance of the wire corresponding to the atmospheric pressure conditions, and this delta P is actually the amount by which we are changing the pressure with reference to the atmospheric pressure. So this is nothing but in other words, I can call it as my gauge pressure. Okay, because we are measuring with reference to the atmospheric pressure, and this B refers to the actually some coefficient which relates the change of pressure with the change of resistance of the wire. Okay, so particularly this type of gauge employs fine wire of manganese, so which consists of 84% of copper, 12% of manganese, 4% of nickel. Okay, and this is actually wounded on a coil, and that coil is enclosed inside a suitable pressure container. Okay, and in that pressure container, then we will be actually subjecting that container to our given pressure situation, and particularly the value of this coefficient B is nothing but equal to 2.5 into 10 to power minus 11 units are in per Pascal. Okay, so that is the value of this coefficient B, particularly when we are considering the manganese wire. Okay, now these type of gauges are subjected to aging over a period of time, so they require frequent calibration. Okay, so from time to time their change in resistance capability will be actually changing. So this value of constant B will not be no applicable after certain period of time. So what we need to do, we need to once again recalibrate it in order to obtain a new coefficient. Okay, then this type of gauges are mainly used for measurement of the high pressure, because if we will be having the more change of the pressure, that will be leading to the significant change in resistance. So because of that, it will be becoming accurate at the high pressure conditions, and accuracy of this type of gauge is actually within the limits of plus minus 0.1%. Okay, and also the transient response of this type of gauge is very good, because it will be significantly changing the resistance or instantly changing the resistance while the condition of the pressure is actually changed. Okay, and you can see over here it is written that this resistance wire can respond to variations, particularly in the range of megahertz of frequency. Okay, but obviously while we are considering this for measurement of pressure in our fluid system, we cannot go up to the frequencies of megahertz. Why? Because fluid system will be having its own dynamic response, and particularly that response will be limited by the speed of sound in that particular fluid. Okay, so that is something which will be limited by the acoustic response of the transmitting fluid. So whatever the acoustic response we will be having of the transmitting fluid, depending upon that, we will be actually getting the overall frequency. Okay, so this particular Bridgman gauge is also used for the high pressure measurements. Now we will talk about some of the gauges which are used for the measurement of the low pressure conditions. Okay, so particularly for low pressure conditions, one of the gauge we are having McLeod gauge. So this is a very popular gauge which is mainly used with the gaseous fluids. Okay, so this is used with gaseous fluids in the vacuum conditions. So what we are having over here, if you see the construction of this gauge, we are having some capillary over here. So this capillary C, then we are having a big bulb over here, B, then some opening B is here, and particularly this opening is then connected to another tube, and inside that tube we are having one more capillary over here. So this particular capillary is actually known as reference capillary, and in this reference capillary we are having some scale also marked over here. Okay, and above this reference capillary we are having one pipe, and this pipe is basically connected to the space for which we want to measure the pressure. Okay, and we are, as we are going for the low pressure measurements, obviously the pressure will be less in comparison to the atmospheric pressure. So this pipe is nothing but connected to our vacuum space for which we want to measure the pressure. And with this we have some movable reservoir. So this movable reservoir also helps us in overall principle of the pressure measurement. So how, that we will try to see over here. And this movable reservoir plus entire circuit is actually filled with some manometric fluid. So let us consider over here that in the present case it is filled with mercury. Okay, so now what is done over here, if we see the procedure of the measurement of the pressure, so what is done with vacuum space. Okay, and after that what we will be doing, because whatever the level we will be having in the reference tube, that level will be rising because of the level of the movable reservoir. Okay, so what we will be doing, first we will be connecting it to the vacuum space, and then we will be lowering the level of this movable reservoir. Okay, so we will now lower the level of movable reservoir, and we will be lowering this level until we are getting the level of manometric fluid till this opening over here. Okay, so what we will be doing, First, we will be connecting this to our space, vacuum space. Then we will be lowering the level of this movable reservoir until we are getting the level of manometric fluid inside this entire unit till point O. Okay. So once our entire this manometric fluid has reached till point O, after that what will be happening? From this vacuum space, whatever the fluid is there, that fluid will be actually entering and it will be filling the entire space which is actually vacated by the manometric fluid. Okay, so this entire space over here, you can see the bulb area and the small tubes. This entire space will be basically filled by our medium which is there present inside our vacuum space. Okay, after that, once the entire medium has filled, after that what we will be doing, once again we will be increasing the level of the movable reservoir and we will be increasing its level till the point our level of manometric fluid is actually reaching to the reference value. Okay, so this is one important point, that first we will be lowering the level in order to fill the entire chamber, this entire space with our medium for which we want to measure the pressure, and then we will be increasing the level of the movable reservoir and we will be increasing till the point we are getting the value in our reference capillary corresponding to the 0 mark. Okay, so while we will be increasing the level of this movable reservoir, because of that what has happened, this entire space over here is actually filled by the manometric fluid, and obviously here what has happened, whatever the medium, gaseous medium was trapped inside this bulb and this capillary, that gaseous medium will be actually compressed in this closed ended capillary, because over here we are having nothing but a closed ended capillary. So in this particular branch of the instrument, what will be happening, when the manometric fluid will be rising, it will be displacing the this particular medium to our vacuum space. Over here what will be happening, whatever the gaseous medium was trapped till this point, particularly inside this bulb, this portion, extended portion of the tube and this closed ended capillary, that gaseous medium will be actually compressed inside this small narrowed portion of the capillary tube. Okay, so because of that what will be happening over here, we can see that here our pressure is P, and in this portion this volume of the gas has been actually compressed. So because of that the pressure in this particular region will be different in comparison to the pressure at this point. Okay, so let us consider now the pressure in this particular portion of the capillary is equal to Pc. Okay, so now if we consider that small a is nothing but area of cross section of this capillary. So small a, what I have done, I have considered C. Okay, so whatever this capillary we are having C, for that we have considered A as area of cross section, and let us consider that Y is the amount of or the length of the capillary where we are having this gaseous medium which is compressed over here. So because of that what we can determine the volume which is compressed over here. That volume will be nothing but equal to cross sectional area into Y. Here Y is the portion which is actually filled with that gas. Okay, and if you try to see the initial volume of this gas, so when we have actually lowered the movable reservoir, at that time this gas was filled actually in this entire portion. Okay, so this entire volume is actually known for an instrument, and let us consider that this entire volume is nothing but equal to Vb. So when the entire gas was filled with this volume, at that point our this entire chamber was nothing but was filled with this medium of the vacuum space. So that's why in this entire chamber pressure was nothing but equal to that of the vacuum space pressure. Okay, so when this entire chamber was filled with the gas, at that time the pressure of the gas was nothing but equal to P, and when this gas is compressed over here, in this case the compressed volume of the gas is equal to A into Y. So we can say that the volume of the gas is now changed from volume Vb to volume Vc. Because of that the pressure of the gas has increased from P to another pressure P. Okay. Now, the scale of the capillary is actually adjusted in such a fashion so that the difference of PC minus P is nothing but equal to Y. Okay. Now, what we can do, we can consider over here that when we have increased the level of the reservoir, there has not been any heat interaction over here. So, we can consider that this compression of the gaseous medium in this bulb region and the capillary region has taken place at constant temperature condition. So if we consider the isothermal compression, so I can simply write that pressure corresponding to volume B into VB will be nothing but equal to pressure corresponding to C into volume of the gas at point C. So this condition we can compression of the gas over here. Okay. So using this formulation, I can find out the value of pressure PC as nothing but P times VB by VC. So now if I replace the value of PC over here in this particular equation, then I can write P into VB divided by, in place of minus P is nothing but equal to Y. So this will be finally becoming P times V into B minus AY divided by AY. Okay, and this will be equal to nothing but my Y. Now, one important point you can see over here, whatever the volume we are having over here, this compressed volume of the gas, VC, this is nothing but very, very small in comparison to the volume of this capillary plus volume of the bulb plus the volume of this extended portion of the tube till opening. Okay, so as our VC is very, very small in comparison to VB, so what I can do, I can neglect this portion, or I can simply write that my VB minus AY is nothing but nearly equal to VB. So from here I can write down the value of pressure as nothing but nearly equal to AY square divided by VB. So where A is nothing but cross-sectional area of the capillary, which is already known. VB is the volume of this instrument, which is also known, and Y is the reading of the scale when it is actually, and particularly it represents the portion which is filled with the gas. So using this measurement of Y, I can simply determine the value of the pressure. Okay. Then let us try to see another type of temperature measurement, pressure measurement device. This particular type of gauge is known as Pirani thermal conductivity gauge. So this case, what we do, we consider a tungsten or platinum filament over here, and we heat this filament. Okay, and this filament is actually particularly enclosed in some chamber, and we actually connect that chamber to our vacuum space for which we want to measure the value of the pressure. Okay, so now what will be happening, depending upon the value of the pressure, there will be change in effective thermal conductivity of the medium. So what I can write over here, that delta P leads to change in effective thermal conductivity of the medium. Okay. So what will be happening if I have some heated filament over here? So this is nothing but a heated filament. So if I have a heated filament over here, that heated filament will be actually exchanging the heat with the this gas which we are having coming from the vacuum space. Okay. So because of that, what will be happening? Initially, we will be having certain known value of the temperature of the filament, and after some duration of time, there will be actually change in temperature of the filament, or in other words, I can say this portion of the gas will be actually taking the heat from the filament, and because of that, it will be actually heating. And finally, we will be having some thermal equilibrium in between our filament and the gas. Okay, so now the time required to attain the thermal equilibrium will be actually changing with change in thermal conductivity of the gas. Okay, and thermal conductivity of the gas is nothing but a strong function of the change of pressure. So depending upon that heat transfer characteristics, we can relate it to the pressure condition of the gas. Okay, so this type of gauge is used in the past for the range of measurement of pressure within the limits of zero point 0.1 to 100 pascals. Okay, and this type of gauge is actually not applicable for measurement of high pressures, because at high pressure conditions there is very little change in the thermal conductivity with change of pressure. So because of that, it cannot be employed for the measurement of high pressure. Okay, and one more thing is there, that it is also not suitable for the transient response of the system. Why? Because this particular system is based on the thermal equilibrium in between the fluid or heat transfer characteristics. So because of the heat slow nature of the heat transfer characteristics, actually it cannot be employed for the dynamic systems or transient systems. Okay. Now in this type of system also there may be one source of uncertainty. So one factor which will be affecting the heat transfer characteristics is the effective thermal conductivity of the gas. At the same point of time, temperature of the surroundings. So ambient temperature will also be having significant control on the uh, heat transfer characteristics of this system. So in order to compensate for the effect of surroundings, what we do, we consider one evacuated container, and inside that evacuated container we use equivalent heat heating filament. So this heating filament will be having the exchange of heat only with the surroundings, and particularly that exchange of heat will be because of the radiation heat transfer. Okay, and over here in this particular type of filament, we will be having radiation with the ambient also, and at the same point of time, we will be having some convection effects in between the gas or this filament, and at the same point of time, we will be having the conduction in between the gas molecules. Okay, so what we will be doing over here, we will be getting actually the overall thermal characteristics, and here we will be getting thermal characteristics only with the surroundings. So if we just subtract the effect of the surroundings from the overall thermal characteristics of the system, then we will be getting the effect of only because of change in conductance or conductivity, thermal conductivity of the gaseous medium, whatever we are having over here. So because of that, we will be able to determine the accurate value of the pressure. Okay, so like we have done temperature compensation in case of strain gauge type devices, we are having here the compensation of the temperature in order to avoid the effect of the surroundings. Okay. Then another type of gauge is there, Knudsen type gauge. So Knudsen type gauge, the construction is like this. So in this, what we are having two fixed plates. So this P type plate is nothing but a fixed plate, and over here also we are having another fixed plate, and this arrangement is actually connected to some suspended filament, and then we are having another movable plate over here. This V is nothing but it represents a movable plate. So over here also you can see another movable plate we are having. So the situation on the right hand side is nothing but exactly the mirror image of the condition whatever we are having on the left hand side. Okay, so over here what we do, we enclose this entire thing inside the chamber, and in between this spacing between that fixed plate and the moving plate, we actually keep our gaseous medium. Okay, and that gaseous medium is nothing but coming from the chamber where we want to measure the pressure. Okay, so now here what we do generally, we keep a very fine or very close spacing in between this moving plate and stationary plate, and particularly this spacing between the plates is nothing but of the order of mean free path of gas molecule. So whatever the gas we are having, depending upon the mean free path of the gas molecule corresponding to the given condition of temperature and pressure range, actually we consider the spacing between the two plates. Okay, now whatever the fixed plate we are having, this P as the fixed plate, both these P type plates are nothing but heated plates. Okay, so because of that, what will be happening, we will be having some of the molecules. These molecules will be first colliding with the fixed plate, and from the fixed plate, because these plates are heated, they will be acquiring certain amount of energy. Okay, and as movable plate is actually having low temperature in comparison to the temperature of the heated plate, so obviously they will be actually the molecules will be coming with high energy and they will be transferring certain amount of energy to the moving plate. So because of that, what will be happening? There will be certain amount of force. So F amount of force will be actually acting on the movable plate, and because of that, that plate will actually try to uh, move away from the fixed plate. Okay, so what we can do over here, we can measure this amount of force which is acting because of the molecular collisions which are coming, particularly coming from the hot plate, and that amount of force can be related to the value of pressure, and this value of pressure is nothing but absolute value of pressure. So it can be related to the absolute value of pressure with using the relation 4 times F into Tg by T minus Tg, where this F represents the force which is acting on the movable plate and Tg represents the temperature of gaseous medium, and this T represents the temperature of plate P. Okay, so this T represents the temperature of plate P, and this temperature T is nothing but greater in comparison to Tg, and this T is maintained by using some heated filament. Okay, and this type of gauge is used for measurement of the pressure within the limits of 10 to power minus 6 to 1 Pascal. The only thing we have to consider over here while we are using this type of gauge, basically our spacing between the plates should be of the order of mean free path of the gas molecules. Okay, so when we go for the measurement of very low pressures, at that time what happens, the mean free path of the gas molecules actually increases, which uh, make it impossible to use this type of gauge for the very low measurement of the pressure. However, this is a very accurate method of the pressure measurement, and many times it is used for calibration of the other type of pressure measurement devices also. Okay, then we have some another type of device for measurement of the low pressures. That particular type of gauge is referred to as ionization gauge. So in this ionization gauge, what we are having, once again, we are having some enclosed container where we allow our gas from the vacuum source to enter. And in this particular arrangement, we are having a cathode, then we are having a positively charged grid, and then we are having a negatively charged plate over here. And this cathode is normally heated over here, and this heated cathode basically supplies some moving electrons over here. Okay, so what happens, these electrons are actually accelerated with the help of this positively charged grid over here, and while these electrons accelerate, these interact with the gas molecules, and within the gaseous medium they lead to the ionization of the particles. Okay, gas molecules. Okay, so what will be happening because of the ionization, the negatively charged ions will be moving towards the grid and positively charged ions will be moving towards the plate. Okay, so because of the motion of the different ions, there will be some current will be developed in the plate side circuit. So the current in the plate side circuit is actually considered as IP, and here because electrons and negatively charged ions are moving towards the grid, so inside the grid also we will be having some current, and it has been observed that pressure is nothing but proportional to the ratio of this plate side current divided by grid side current. Okay, and this pressure is nothing but related to 1 by S times IP by IG, where this S is known as the sensitivity of the gauge. Okay, so S is considered as the sensitivity of the gauge, and the value of S is equal to 2.67 kilopascals inverse. Particularly this value is for nitrogen, then we are having nitrogen as gas over here. So this gas, if it is nitrogen. Okay, so for nitrogen, its value is 2.67 kilopascals inverse. And moreover, this type of gauge is used for the measurement of pressure from 0.13 to 1.3 into 10 to power minus 6 pascals range of pressure. So it is used for very low pressure measurement, because when we go for the high pressure measurement at that time, what will be happening for ionization, we require more amount of heat to supply on the cathode. So because of that, there are chances of the burning of the cathode filaments. Okay, so because of that, it is also employed for very low measurement of the pressure. Then apart from that, based on almost the identical principle, we are having one more gauge which is known as alphatron. So alphatron offers advantages over the ionization gauge, because here we are not having heated cathode for generation of the electrons in order to create ions. Rather, here we take some radium source, and this radium source will be actually emitting alpha particles. So it is basically uh, employed on the principle of radioactive alpha particles. So this radium source will be giving alpha particles, and these alpha particles, while they will be interacting with the gases, these will be ionizing the gas molecules. And then we are having over here one ion collector plate. Okay, and this ion collector plate will be actually collecting the ions. Now, depending upon the collection intensity of the ions, there will be flow of current in the circuit, and because of that circuit, we will be measuring the voltage across this load resistance R, and depending upon this value of the EO, we actually determine the value of pressure. Okay, and you can see over here, this type of gauge is actually used for the measurement of very wide range of pressure. So you can see over here, it is employed for measurement of pressure from 0.1 pascals to 10 to power 5 pascals. So it means it can measure the pressure close to the near atmospheric pressure situation also. Okay. So this is a typical representation of different type of gauges which we have studied, and the corresponding range of applicability of their pressure measurement is also included over here. Okay, so you can see that ionization, Pirani, and McLeod gauge are particularly used for the low pressure measurements and below atmospheric pressures. Then we are having manometer, piezometric, bellow type gauges, which are used for the moderate pressure range, and for very high pressure range, when we are having electric resistance, Borden type, and diaphragm type gauges. Okay. So with this particular lecture, we complete our discussion on the measurement of pressure. Now, what we will do in our next lecture, we will start our discussion of the flow measurement devices.